JSTorch. This is a JavaScript library specifically for machine learning. It was written from scratch, and they built it intentionally to model after PyTorch's syntax. Now, this is closely following PyTorch. It can't be exactly PyTorch's syntax because you get kind of a lot of extra goodies and syntactic sugar with Python being able to overload operators that allow it to be a little bit easier to build, so you can add matrices with the simple plus sign. However, instead, with this, for example, you have to use torch.add. So it's not as simple as a plus sign where you can add two matrices or multiply two matrices together or perform a dot product against two matrices. You have to use this format. So it closely matches up to a point. I didn't want to start off right away with like the problem of what I'm currently looking. There is a problem here. We got to check this out. Look, all right. So we've got some big problems. We've got two major problems. One, it's branded JSTorch. Okay, that's fine. The library repository is also JSTorch. However, it's built to monitor. It looks like PyTorch's syntax, right? That's what they're going after, is PyTorch's syntax, not necessarily LibTorch's syntax. So we've got an underlying LibTorch that's written in C, and it's built specifically to take advantage of hardware acceleration like GPUs and other types of hardware like FPGAs and TPUs. However, this is not, it doesn't use that library. It does not use LibTorch. It is 100% written in JavaScript, JSTorch, and it is only CPU bounded by a single CPU as well, right? So you don't really get the acceleration of multiple cores. You don't get the acceleration of hardware through GPUs, FPGAs, and TPUs. So you don't get to use LibTorch, which is that really powerful underlying performance capability. This is just a from scratch written CPU single-threaded implementation. Now, they did a really good job. They did a really good job of implementing this because it's really simple, right? We see how simple it is. They make it really easy to use, and it does follow all the patterns that you would write line for line in LibTorch or PyTorch. And as you can see here, when you're referencing it as a library or package on NPM, it's listed as JS PyTorch, even though the repository's name is JSTorch and the branding is JSTorch. There's a missing Py in there, PyTorch. So JS PyTorch is the name. So if you look at the package JSON file here really quick, it looks like it is going to be called, yes, the name is JS PyTorch, not JSTorch. So you gotta watch out for that if you want to use this library. It is a JavaScript-like library for PyTorch. They did a good job. I have to say, they did a really good job on that part. But beware, if you want to use this library, npm install js-pytorch. We're taking a look at PyTorch, but not in Python. We're looking at it in JavaScript. So JS PyTorch. This is a library you can install on NPM. Guess what? They wrote it purely in JavaScript, TypeScript compatible. And actually, is it all types? I think it's actually all TypeScript. Yep, just TypeScript. The entire thing is TypeScript, which is nice because you get these abstractions, some cleanness here. Oh, look at all our exports. Okay, so we get a whole bunch of math-based functions that we can use to generate matrices, multiply matrices, connect them, activate them. Oh, and embedding. All right. Oh, we get dropout. Of course, we get softmax for training, dropout for training. So these are great items here for training, and loss, gradient descent. The repository itself, let's see here, it comes with an assets folder with the demo. Ooh, we got to check out the demo here. We also got our source code. Here's the great part that I like about this. This is very simple, clean, few files. Directory structure is phenomenal. Really take a look here. The source directory just separated into 1, 2, 3, 4, 5 files. A+. This is the way all projects should look. How clean is this? This is super simple. I love it. Very nicely documented. All of it is in TypeScript format. This is great. Very clean. Oh, it even has positional embedding. Oh, that's really nice. Look at that. So, okay, so this is great. So it comes with all the necessary sort of math functions that you're going to need to use on a common basis when you're building your own models. I'm gonna read this really quick. Positional embedding. What do we got? You know, this is not exactly what I was looking for typically with a positional. You know, I guess it says positional, so I assume there's going to be some sort of aspect during the embedding in the weights that we're going to see some sort of significant gradient stepping occur, and I don't see that here other than potentially the time steps. Okay, it's actually pretty interesting. processing, we're going to create a layer based on the number of steps that you want, right? Some plateaus or along those lines. It's going to create a randomized a matrix that's going to be assigned. That is actually pretty cool. So like positional encoding might be familiar, where you'll have every other token, essentially, right? Every other token input will be offset significantly by some sort of degree, and that degree will be toggled back and forth between odd and even positions. But in this is kind of a neat approach where you can have a number of different time steps. Not what I was expecting. All right, anyway, jumping back, just taking a look at all the rest of the files here, we have everything we need to actually build a fully working AI model using modern algorithms, right? This is fantastic. Even comes with tests. Let's just take a look at the tests real quick, and we'll see how well we're testing. All right, I count this as pretty decent. Pretty decent coverage. Pretty nice that they also have a benchmark in here as well, so you can kind of get what the performance is. You know, it's really neat because this is sort of optimized on a single CPU. You're going to find that for common, even smaller, medium-sized models are going to perform a lot faster, even though this is single core, not hardware accelerated with GPU. That's pretty interesting because most of these larger framework, like TensorFlow, for example, right? TensorFlow is a huge framework that works really well if you distribute it across a large number of hardware servers and GPUs, and it's kind of optimized for that. However, if you're building small and medium models where you might have millions of parameters, millions of weights in your model, when you're training it, TensorFlow will go kind of a lot slower because it's just not able to parallelize it as much. It's just built for larger projects. And you're actually going to find that many of the use cases you'll be able to train pretty quickly using JSTorch with how clean and simple it is. I know this firsthand because I've done it myself, and it actually is pretty fast. Looking at JSTorch, we have a neural network demo that they're going to give us here. They actually have written a demo that's you can run in your browser directly, leveraging the JSTorch library, which is actually JS PyTorch. Not to be confused where we've got two languages in one, right? Two abbreviated language, JavaScript and Python. And Torch, which is a C-based library that Python uses. It's only JavaScript, and it's pure JavaScript, and it's specifically built for JavaScript to sort of match the PyTorch syntax. I mean, kind of. But let's try out their demo. They have a neural network demo here that lets us modify hyperparameters with a GUI. So we got our training parameters, the hyperparameters, right? The number of layers, and I assume the number of units in each layer. The batch size. Oh, we've got images 32 by 32, fake images, I'm guessing. And the output is 0 to 31. So we don't know what the training set size is. It's just invisible. I guess we could check out the source code really quick. Oh, it's infinite, right? Is that what I'm looking at here? So when we're generating a batch, it'll really add instances to batch. We are randomly generating data on the fly. Okay, that's fine. This is all, toy data. So infinite data. Perfect. So it's going to be hard to converge in that case, right? It would be, as the longer you train it, you won't be able to hit, zero loss. Obviously, you don't want to hit zero loss in most of the cases, but there's no way to really know. With infinite data, you need infinite layers and infinite units. So we'll just stick with one layer, 10 units, batch size. Let's take that down to 4 and train. We'll click train. Okay, so we're going through iterations here. It'd be nice if it also showed the epochs, but we don't know how big our data set is, so essentially you'll never hit one epoch. And as you see here, the line will start lowering as it gets closer to 0, which means that it's learned everything it possibly can. For all the data that we've shown it's learned as much as it possibly can. And essentially, it's getting the data. Every prediction is 100% accurate once you've hit this here. So this is going to take a really long time because our learning rate is pretty low. Let's see if we can. Let's improve this learning rate here really quick. Let's go crazy with our learning rate train. All right, so now we should have a faster conversion down towards 0. So you can see our loss here is kind of randomly flickering around. It should start going below 2, I would expect. Because the learning rate is crazy, we're seeing higher jumps, but it's able to learn faster. Also, since the data is random, it can only go so far, but it's still learning, and this is all done on using one core of a CPU. it won't go any better. It could go faster. So we did pretty good here. We've got about 1,000 iterations. We'll pause here right around 1,000. We got to roughly around 2-ish, a little bit below 2 on the loss, right? Which you want to get as low as you can, depending on what you're looking for, right? Depending on what your model output is, right? Are you targeting, organic data, like image data that you're going to be taking, and it will be widely varying, right? So if you're taking pictures out in the world, you could basically have any random picture, and you want this model to be able to predict or understand something about the photograph, right? Whether the photo is taken inside or outside. That would be like one example. You would want this to converge as low to 0 as possible. Now, if you want it to do things like image detection of items in the frame, you would have a much larger output possibilities range of all possible objects in the dictionary, and then you would create training data samples to like there's a cat or a dog, or there could be cat and a dog in the photo all at once, but the cat and dog could be in many different positions. So you don't necessarily want a perfect 0 because you're going to be taking organic photos, and in that case you want more generalization. So I added a few more layers, same parameters. Oh, wait, stop. We got to make sure that our training rate is the same. So we added 2 more layers, right? So we got 2 more layers here, same number of units, same learning rate and batch size as before. And we should be able to learn a little bit better because we have got more parameters, right? More weights in our model. So we'll be able to learn more data. So you can see it's converging a lot faster. It's able to retain more information because it's got more memory, right? We've got more memory here to learn things. And so our loss is going to go down lower more quickly. All right, we got about 1,000. So we roughly doubled our performance of the model. The loss is roughly half. And it did start converging here with the diminishing returns, with just adding 2 more layers, right? That's the deep learning aspect of it. It can learn more because it's got, it can make more connections in the fully connected layers, and there's actually more parameters for it to learn, right? More memory. So it does the trick. It's actually working the way it's supposed to. This is fantastic, and this works really well. I mean, you can imagine leveraging this kind of technology maybe in a browser or even in a smaller project to learn things in a very specific domain. You don't need that much compute power, and if it's a small amount of data in a small domain, you can create an AI model that gives you very accurate information. Perfect use case is, say, assembly line, where you've got a factory conveyor belt that's looking at produce, and you want it to quickly detect whether the produce is ripe or it might be spoiled produce. You can have an ejector capture the XY coordinate and then toss it out. One of the quickest examples we can see for machine learning and artificial intelligence is a demonstration provided to us by JSTorch. JSTorch is that library, that JavaScript library, that kind of closely references PyTorch's syntax. Now, it's not exactly the same because you have to use syntax that looks like this, right? Where you torch.add, instead of just saying out plus B, you have to say torch.add out and B. But it's still all the same from a line perspective and a sort of a functional based perspective. So we start by importing our JS PyTorch library. Then we define 3 matrices. The first matrix, this seems like the input matrix. X, typically in machine learning, kind of a standard on the industry, has always sort of standardized on X being the input data, and Y would be the output data. Or you could just call it out, right? W would be the weights. This is the brain, the memory, typically the weight parameters. But we also have a different kind of weight called a bias, which will be B. And B is typically not multiplied onto in between matrices, it's added, right? So it's an additive to shift things up or down based on a bias. So we create a random matrix here. It looks like we've got 8 samples in a 4x5, and then we've got, the inverse, which is a 5x4, and another 8, and we are going to require gradients, which means to me that the tensor object here that we're getting back is going to have another matrix that's specifically able to hold details about the deltas between its layers, which is the gradient. Same for the output layer here, or the bias layer. We also need to remember our gradients. So gradients are used during the training process. So this is very much going to be a training example, not an inference example. During inference, you don't need gradients. So as you're initializing the model, you would just say false, or the default might be false. by default. So you wouldn't need these gradients. It would save memory essentially because you don't need that. So let's go ahead and do one pass on this. We're going to make a calculation to matrix multiply x and w. So our input data, right, which could be a photograph or a sentence, and then we multiply it with our model's weights, which is the memory, the brain, right? And this gives us an output. Now we're going to pass that forward to our bias layer, add the bias to it. Then we can compute our gradients by running out.backward, and this will store the gradients in our W and our B. And then we can print those gradients, which tells us the delta or difference they are between each of the layers. Then we can use that information in a training cycle to then back propagate, optimize each of these matrices based on a learning rate. So we essentially like subtract or add, you could go either direction, the delta. And then but before you do that, you don't want to do 100% of that delta, because then you would, well, I mean, you could though, like say if you didn't have a learning rate, the learning rate was 100%, you would be able to get the model to perfectly predict the input. It would say, yeah, I've seen this before, this exact input means this. But then the model wouldn't be super useful. You'd only be able to determine if you've seen this one thing. And you kind of want this model to be general purpose so it can see similarities between different inputs, because you want it to work for you. So we're taking a look quick here at JSTorch, and guess what? It doesn't use LibTorch. I was looking at some of the issues. Like one of the things in the issues here, I'm just looking at the screen. We've got a couple of enhancement GPU support, and you're like, wait a second, hold on, timeout. JSTorch kind of makes you think, even though the library itself says JS PyTorch, that it uses LibTorch underneath. It doesn't. It's just specifically helping match the PyTorch-like syntax. Now this, let's see here, we have a developer. It's not an issue, it's just saying that we want, for hardware acceleration, we might consider GPU.js. Now, GPU.js is a legitimate hardware accelerated, I guess, math library that you can leverage in JavaScript in a browser and in Node.js to leverage your GPU to accelerate any kind of math operations, because your GPU is able to process massively in parallel multiple math operations all at once, which is perfect for matrix multiplication and even activation layers. And it's so cool. They do such a good job. I want you to check this out, because I've used this before firsthand, and it is wonderful. You can create your own GPU math function, and this function will get transported over your GPU and compiled, and then you can transmit your matrix via textures, and then for every pixel in your texture, it can run this function and give you an output. So it's really cool that you can do. This is a matrix multiplication, for example, a simple GPU where you've got, you get 3 threads. You get 3 threads all together. You get an X, Y, and Z thread, which allows you to sort of splay out all of those math operations across a 3-dimensional array of, I guess you call them tensor cores, right? Or general purpose compute cores, the shader cores in your GPU. And if you have 10,000 shader cores, or compute cores in this case, then if you can essentially take this 512 by 512, which is roughly 262,000 operations, 512 by 512. But they've also added another one in here, for example, of doing this 512 times. So you've got 512 by 512 by 512. You multiply that by 512. And now you've got 134 million operations, which would take a long time on a CPU. But with a GPU, you would be able to achieve this pretty quick within, just a short number of seconds, whereas a CPU would take minutes, if not hours. So this is actually a really nice issue, and the cool part is they can incrementally add acceleration for each of these operations. Looking at the source code, you could pretty quickly just start writing these kernels and then incrementally adding these for each of the different equations. Now here's the extra bonus part. With GPU.js, you can write a kernel that does a whole bunch of stuff all at once, including the activation and the matrix multiplication and the bias addition all at the same time. Now that's really powerful because you can do things that are really fast. Now all that compute is going to occur without you having to transport memory between the bus on the CPU, the RAM, and the GPU's memory. You can just put everything over to the GPU. The GPU can just, run really fast and process all that data, and you can create a mega kernel. They also have, and in case you don't want to do that, right, because you might want to have a flexible framework, they have a sort of a pipeline which allows you to pass in your model all together, right, each of the layers, and then allow you to process the output between a pipeline of equations between kernels. So that way you don't have to keep between each of the phases, each of your training processes. You don't have to transit that memory output back to the CPU and then back to the GPU and then back to the CPU again, because it's the slow part. If you can keep everything on the GPU, then this is going to be really, really fast. So it's actually great. It supports TypeScript. So actually in this case, you could have eventually a hardware accelerated JS Torch library.